Hey folks, this is the Crazy Hat Chemist, and this is the fourth video in a series of 16 on gases. Today we're going to be talking about a manometer and calculations therein. So here we go. This is a diagram of a manometer. There's a round bottom flask filled with gas. There's a stopcock. That stopcock is open and it's attached to a U-tube. So the pressure in the flask of this gas is 0 atmospheres. There's a closed end to the U-tube. There's a vacuum on the right-hand side of the U-tube. There's mercury. All that gray stuff there that you see is mercury. You should see that the two levels of the mercury in the right end of the U-tube and the left end of the U-tube are equal. That means that the following. The gas pressure in the round bottom flask is equal to the gas pressure in the vacuum. All right, let's do another example. Here we go. Same manometer setup. We have an open stopcock again, just like before, but this time we have the pressure in the round bottom flask at 1 atmosphere pressure. The closed end of the U-tube is still there. There's a small vacuum in this one, just like before, and there's mercury. The mercury is the gray and the yellow this time. You should see that the level of mercury is higher in the U-tube, on the U-tube side, on the right-hand side, compared to the round bottom flask. This means the following, that the gas pressure in the flask at 1 atmosphere is equal to the additional height in the U-tube. So that U-tube height is equal to 1 atmosphere of pressure. Let's do another example. So an open stopcock again, just like we had before. We have 1 atmosphere pressure of gas inside the round bottom flask. There's mercury. You should see that the levels of mercury are equal on the U-tube on both right and left hand side. What's different on this example is that there's an open end at the U-tube, so it's open to the atmosphere, so atmospheric pressure is pushing on there. So what does this mean when you have the gas pressure in the flask at 1 atmosphere and it's open to the atmosphere on the U-tube end? It means the following, that the pressure in the flask at 1 atmosphere is equal to the atmospheric pressure, and that's also 1 atmosphere. All right, let's do another example. Another example, we still have an open stopcock with the gas in the flask here, and this time the pressure of the gas in the flask is 2 atmospheres, so that's a little bit different than all the other previous examples. This is still mercury, the gray and the yellow is still the mercury, and the level of mercury is higher on the U-tube side, you should see that. Then the height of the mercury that's above the equal levels of mercury in the U-tube is 760 millimeters. And this is measured with a meter stick, of course. And this means the following. The pressure of the gas in the flask is 2 atmospheres is equal to the atmospheric pressure pushing down plus the additional height of the mercury, and that's 760 millimeters of mercury. So that's why 1 atmosphere of pressure is equal to 760 millimeters of mercury in terms of height. So now let's do a mathematical calculation with this. So you should see the diagram on the left-hand side. This time we do not know the pressure of the gas inside the flask. We know that the U-tube is open to the atmosphere. You should see that the height of the mercury is higher on the U-tube side that is open to the atmosphere and lower where the round bottom flask is. We actually have measured the height of the mercury in the U-tube at both ends. So let me read the question for you as you follow the diagram. A laboratory barometer reads an atmospheric pressure of 764.7 torr. That's the atmospheric pressure. A sample of gas is placed in the flask attached to an open-ended mercury manometer. See the diagram. A meter stick is used to measure the height of the mercury in the 2 arms of the U-tube. What is the pressure of the gas in the flask in atmospheres and in kilopascals? So really what we're trying to do is solve for x here. Hopefully you see that x. That x is the difference in height between the total height of the mercury on one side of the U-tube and the height of the mercury on the other side of the U-tube. So we're going to have to take a difference of those two heights to get the height of the level of the mercury there. So, same diagram. Now this is associated with the math solving for this problem. We are solving for x just like before. So the pressure of the gas in the flask is equal to the atmospheric pressure plus the additional height of mercury that in the U-tube. So the atmospheric pressure was measured with a barometer at 764.7 torr. That was given in the problem. And then the difference in the height of the mercury at the two ends of the U-tube, and that is 136.4 torr minus 103.8 torr. You should also understand that millimeters of mercury and torr are the same number, right? 760 millimeters of mercury and 760 torr are actually the same thing. So this value gives me the pressure of the gas in the flask, and that is 797.3 torr. Now what we need to do is convert this into the other units that are given in the problem. So we're going to take that 797.3 torr and convert it into atmospheres. So I'm going to use the unit conversion of 760 torr to 1 atmosphere, and I get 1.049 atmospheres. You're always looking at significant figures. The significant figures in the problem that I had before was 4 significant figures because there was 1 decimal place in those previous calculations. And the unit conversion of 1 atmosphere in 760 is an infinite number of significant figures. So that's why there's 4 significant figures in the 1.049 atmospheres. Now we're going to convert those atmospheres into kilopascals. So this is the 1.049 atmospheres, converting it to kilopascals. 1 atmosphere, infinite number of significant figures, is equal to 101.325 kilopascals. And again, we get the same number of significant figures that we had in the previous number. That's 4. And so that's why it's 106.3 kilopascals. If you didn't like that unit conversion, you could have actually stayed with the 797 torr and converted that into kilopascals. So that's right here down at the bottom. That gives you that example, and you still come up with the same answer. So that is 797.3 torr, and converting the torr into kilopascals, the 760 torr and the 101.325 kilopascals also have an infinite number of significant figures. So the 106.3 kilopascals is the same no matter which unit conversion process you use. So when you go to a conference, and I don't know if you've ever been to a conference, what do you want? You want sulfur, tungsten, and silver. And why is that exactly? Because if you use those elemental symbols, that is swag, and you always want more swag. So that was the 4th video in a series of 16. Make sure that you preview the previous 3 videos so that you understand how to do those unit conversions. Look for the next video. That's video number 5, and we're going to be talking about the combined or the general gas law. I will see you then. Bye.